Brad Williams, interest rate parity and cost of carry model. In essence, the IRP theorem is simply the exchange rate equivalent of the cost of carry model. To see this equivalence, consider the cash and carry strategy for the interest rate market. In a cash and carry transaction, a trader follows the following steps: borrows funds and buys a bond, carry the bond to the futures forward expiration, and sell the good through a futures forward contract arranged at the initial date. The cost of carry is the difference between the rate paid on the borrowed funds and the rate earned by holding the bond. Our familiar cash and carry strategy is known as covered interest arbitrage in the foreign exchange market. In covered interest arbitrage, a trader borrows domestic funds and buys foreign funds at the spot rate. The trader then invests these funds at the foreign exchange rate until expiration of the forward futures foreign investment back into the domestic currency. The cost of carry is the difference between the interest rate paid to borrow funds and the interest earned on the investment in foreign funds. Thus, a trader borrows the domestic currency, DC, at the domestic rate of interest, DC, and exchanges these funds for foreign currency, FC, at the spot exchange rate. Trader receives DC divided by FC units of the foreign currency and invests at the foreign interest rate, FC. This rate, RFC, is the interest rate applicable to the time from the present to the expiration of the forward or futures. At the outset of these transactions, T is equal to 0. The trader also sells the forward or future contracts at F of 0 for the amount of funds, DC divided by FC times 1 plus FC. With these transactions, the trader has no net cash flow at T equals 0. At expiration, the trader receives DC divided by FC, 1 plus FC units currency against the forward or futures contract and receives F of O at time T in the domestic currency. Trader must then pay the debt on the original borrowing, which is DC times 1 plus DC. If the IRP theorem or equivalent, the cost of carry model holds, the trader must be left with 0 funds. Otherwise, an arbitrage opportunity exists. Applying this notation to our previous examples of the cost of carry transaction, 180-day horizon, we could generalize this example to write an equation for the IRP theorem or the cost of carry model as it applies to foreign exchanges. For convenience, we begin with $1 as the amount of the domestic currency, DC. Earlier, for our example, we wrote 1 times 1.20 times 0.05 is equal to 1 divided by 125 times 1.3697.05 times 1.17, and we get 1.0954. Got that? Here it is. In the new notation, this translates as follows. DC, this is going to be your cost of carry. DC times 1 plus DC is equal to DC divided by FC times 1 plus FCF. Remember that the DC and FC are the interest rate for the specific period between the present, T equals 0, and the expiration, T. Isolating the future price on the left-hand side gives equation 9.1, F of O equals DC 1 plus DC divided by DC over FC times 1 plus FC, which is equal to this right here. Equation 9.1 says that for a unit of foreign currency, the future price equals the spot rate of the foreign currency times the quantity. F of 2, 1 plus DC divided by 1 plus FC. This quantity is the ratio of the interest rate factor for the domestic currency to the interest rate factor for the foreign currency. We can compare this to our familiar equation 3.33 for the cost of carry model in perfect markets with unrestricted short selling. F of O, S equals S times 1 plus C, where F of O T is the futures or forward price at t equals 0 for an exchange contract to expire at time t, S of O. S of O is the spot price of the good at t equals 0, and C is the percentage cost of carrying the good for t is equal to 0. So equation 3.3 and 9.1 have the same form. Therefore, the quantity in equation 9.2 equals 1 plus the cost to carry, 1 plus C. Cash and carry strategy requires borrowing at the domestic rate, DC. So this is an element of the carrying cost. However, the borrowed domestic funds are converted to foreign currency and earned at the foreign interest rate. Therefore, the foreign earning offset the cost being incurred through the domestic interest rate. The net result is that the quantity of equation 9.2 is the value for 1 plus the carrying cost. As a similar approximation, we note that 1 plus cost to carry equals 1 plus DC divided by 1 plus FC equals 1 plus DC divided by 1 plus FC. Therefore, the cost to carry approximately equals the difference between the domestic and foreign interest rates for the period t is equal to 0 to futures expiration. To complete this discussion, let's apply this equation for the 180-day horizon using the rates in table 9.4. We have already seen that there's no arbitrage possible for this horizon. For this example, we have the following data. F of O t is equal to 1.17, S of O is equal to 1.25, DC is equal to 95445 right here for the half year, and F of C equals 7.1734. Here's the formula. There's the 1.17. The equation holds exactly the cost to carry, negative 0.64. For this example, the approximate cost to carry for the half year is 9.54 minus 0.17347 equals this number here. Thus, the cost to carry for the half year is approximately 0.075. The cost to carry is negative because the cash and carry trader pays at the domestic rate but earns interest at the higher foreign rate. For the same reason, the future price of the foreign currency must exceed the spot rate. If the foreign rate of interest had been lower, the future price of the foreign currency would have had to be lower than the spot rate to avoid arbitrage. Yep. Welcome to Finance 2.0. We're stepping into some complexity here. I'm going to have to work through this particular example and explain this as we move forward, okay? This is rather forward-looking. I have 3 more examples that might clarify this. We'll see. Brad Williams, Frugal Finance. Thanks for watching.